In this section, we will very briefly cover following topics. One is piezoelectricity in textured oriented ceramics. Second, piezoelectricity in quartz with just one example, and we will talk about quartz later on more when we discuss applications. And also piezoelectricity in aluminum nitride and hafnium oxide based materials in which ferroelectricity has been discovered very recently. So we'll start with textured oriented ceramics. Now you remember when we discussed symmetry of piezoelectric materials, we said that if you have a polycrystalline material with randomly oriented grains, then the only way to have a piezoelectricity is having this material, polycrystalline material made of a ferroelectric, and then by applying electric field, we can reorient domains, polarization vectors in that material along the field and break the spherical symmetry, get conical symmetry, and induce piezoelectric effect. I also mentioned that if we manage to make ceramics polycrystalline material with textured grains, so that polarization or direction in which material is piezoelectric is all, or in majority of the cases, oriented in the same way, then we can in principle make piezoelectric any material. We can make polycrystalline materials of any piezoelectric material piezoelectric without need to pole. So this has been done in several cases, notably in lead magnesium niobate. How would this work? First of all, in a polycrystalline thin films, it is much easier to get orientation, to get a texture than in bulk ceramics. We are working with the thinner layers. If we can control, nucleation of the grains and so on, we often get textured, some preferential growth of grains. You remember the case of zinc oxide that I showed you at the beginning. Zinc oxide tends to grow in these columnar shapes. It's a pyroelectric material, but not ferroelectric. However, in these columnar films, thin films, it often gives net polar response and therefore piezoelectric effect. PMNPT and PZNPT would be very interesting. These are especially on the rhomboedral side, where we have this very large anisotropy in piezoelectric coefficients in crystals. And you remember what I said when we discussed these crystals and morphotropic phase boundary, that in these relaxor ferroelectrics with the rhomboedral symmetry, the largest piezoelectric coefficient is along non-polar direction. And that's because we have this large effect of polarization rotation. So if we can grow crystals in such a way that majority of them are oriented in this direction, and then we apply electric field to polarize it, we could get a much larger response than if we make normal ceramic and polarize it. So that's another aspect of this use of textured oriented ceramics. We still use a ferroelectric material, but can increase the response if we can have grains all oriented in the same way. As I said, in single crystals, in thin films, this is relatively easy, but much more difficult in ceramics. And if we have a normal ceramic, let's say of PMN PT, the grains are all oriented in different directions, and we can still make this piezoelectric if we apply external electric field. But the response will be relatively small with respect to that in the crystals. However, if we can orient all grains to be in the same direction, and for PMN and PT, it should not be direction of polarization, but under an angle of about 50 degrees with respect to polarization. So they are all oriented in this direction. Then by applying electric field, polling material, and then by applying electric field to measure, we can get a response which is much bigger. So D33 much bigger than D33 in ceramic with the random grains. And still smaller than that in the single crystals, but much larger than in ceramics with randomly oriented grains. Now here you still have to, if you make, for example, orientation grain-oriented ceramics out of zinc oxide, then all you have to do is apply your pressure or a measuring field. You don't need to pole it. You cannot pole it because material will not switch polarization. It's not ferroelectric. Here, in ferroelectric materials, you would still have to pole material to get a maximal response, and that's because you would have some domains. So if you take this case here, for example, some of these polar vectors could have been oriented like this or other 4 directions, and therefore we still need, or some of them like this and some of them like that, and we would still need to polarize material. So the texture here actually helps us not that much getting piezoelectric effect, but getting exceptionally large piezoelectric effect using this property of polarization rotation. So how can this be done? Where there are several papers by Gary Messing from Penn State and Susan Trollier-McKinstry, which you can look for. They tried different materials, not just PMN, PT, especially Gary Messing. What they did was to put single crystals of other materials such as barium titanate or strontium titanate in the ceramic matrix, and then heating it at high temperature. And then what you find out is that these grains will start growing around these seed crystals and give you textured material. And this works reasonably well. Another possibility is to make this whole ceramic single crystal. If you have all these grains growing in the same direction, it is possible that grain boundaries will disappear and that you will get one big grain around your seed grains. Now, using seed grains helps texturing, but it is also undesired because you are introducing another composition. So you have to carefully control how much of these of these seed crystals, if they have different chemical composition, you put inside, not to destroy property or reduce property of your material. Getting the whole ceramic transforming into single crystal has been done by several groups. I'm sorry, I cannot right now remember the references, but they are in South Korea. I think people in IEEE did this. One of the Korean companies that is growing PMN PT crystals and PZN PT crystals is also, I think, if my memory doesn't fail me, is also growing these crystals out of ceramics by using seeds. Here is an example that was done on potassium sodium niobate, where we have a potassium sodium niobate template crystal in a ceramic of the same material. So here there is no problem with chemical composition, and heating this in at a high enough temperature, we got crystal growing around it. So you see that after some time, the grown crystal out of ceramics, so the grains are fused and then they reorient and start growing in directions dictated by this crystal. You see here domains and the grain boundaries more or less disappearing. This was done by a group in Institute Josef Stefan in Ljubljana. So this is an interesting way to maximize the properties. There is a famous work by Saito and colleagues, and from Toyota Research Central Research Lab, and their famous paper in Nature. That was either 2004 or 2005, in which they grew potassium, sodium, lithium, niobium, tantalate crystals, and by making templated grain growth, textured ceramics, they were able to get properties which are comparable to those of PZT. Of course, it's a complex process, can be expensive, but this can be done. I think Siemens has tried the same approach, and they also get potassium niobate based ceramics with oriented grain size, which give properties similar to those of PZT. I'm not sure how viable this is commercially, whether you can make the same amounts of these textured ceramics as you can normal ceramics, but that remains to be seen. The other topics that I would like to cover here is properties of a quartz, which can be used only in a as a single crystal, and quartz has a very large anisotropy. It's very interesting material in that respect. It's I think first piezoelectric material, and has been used already since 15, or maybe that was TGS. I should not go into this. So what I want to say here is that one of the applications of quartz is for timekeeping, where you have a quartz resonator. So this is something like acoustic fork, which oscillates with a certain frequency. You count number of oscillations per second, and that's basically your resolution for the timekeeping. And these quartz resonators are widely used in quartz watches, electronic watches, and they are much more precise than the most expensive mechanical watch. Now, why quartz is interesting for this? Well, you see how crystal is growing, and it turns out that crystal cut along one of the principal axes is not the best for frequency applications, because as you know, the resonant frequency is proportional to elastic compliance, or directly proportional to Young modulus. And you want this resonance frequency to be stable with, for example, temperature. You wear a watch, and if you go outside from a room in which temperature was 20 degrees, you go outside where temperature can be plus 40 or minus 20. You don't want this resonance frequency to change. So you need to work under stable conditions where resonance frequency doesn't change very much. And the parameter to control is elastic compliance. Other parameters such as density, of course, are not going to change that much. So there are what is called different cuts in a crystal in crystals of quartz, where elastic properties will be a sum of elastic properties along these principal crystallographic directions. Some of them will be negative, have negative temperature coefficient, would decrease with increasing temperature. Some of them would have positive temperature coefficient, increase. Elastic constant would increase with increasing temperature. And since the elastic constant under some angle is a function of elastic constants along principal axis, different ones, and if these have different temperature coefficients, you can find a cut where this elastic constant has almost zero temperature coefficient. And you see that here, this is the change of frequency with respect to value of resonance at room temperature. So that's temperature coefficient. So that would be change with respect to that. So let me do this correctly. So temperature coefficient is room temperature and how much it changes with the temperature around that point. And you see here different cuts. Around that, I think this is this AT cut or something like that, and you see that you can get something which is relatively constant here in a temperature range where you use your materials. You will find very often in electronic equipment that its best operation temperature is between, let's say, 0 and 30, 40 degrees or something like that. And one of the reasons is that many components have properties that will change with the temperature. So in a single crystals, you can control this by making different cuts. So here is one of the examples where these Euler transformations are useful. If you know crystallograph values of, let's say, elastic compliance along crystallographic axis, then you can calculate along what would be a value along arbitrary direction. And if you know temperature dependence along crystallographic axis, that will also give you temperature dependence along arbitrary direction. So you don't have to measure every time. It's enough to determine this along principal directions, and then you can, with the Euler transformations, you can get it in other directions. Now, you mentioned many times that actually we have very few piezoelectric materials that are commercially used besides PZT, which cannot be used in a single crystal form, PMNPT, which can be used both as a single crystals and ceramics, lithium niobate, which is mostly tantalate, lithium tantalate, which are mostly used as single crystals. Almost anything can be done in a form of thin films. There, since several years, new crystals that have appeared, which show very interesting either piezoelectric or ferroelectric properties, and as ferroelectric, they also must be piezoelectric. And I would like to mention here two of them. One is aluminum nitride, doped with scandium, and the other one is hafnium oxide. So if you're interested in a hafnium oxide, it's a derivative of fluoride structure. Fluoride structure is, I think, FM3M. So it's not piezoelectric. And the group in NEM lab in Dresden has done a great job in first in discovering ferroelectricity in this material. Of course, structure is no longer fluoride, but it's based on that, and that ferroelectricity appears in very thin films. Being ferroelectric, that material is also piezoelectric, and I think this group is also testing hafnium oxide and its derivatives for piezoelectric applications, for energy harvesting, pyroelectricity, and so on. The advantage would be that it is lead-free. Hafnium oxide is known material in semiconducting industry as a high K, high dielectric permittivity material. ALN as a piezoelectric material has been used for many, many years. It's very stable. It has a very stable piezoelectric coefficient up to very high frequencies, and even though its piezoelectric coefficient is 2 orders of magnitude smaller than that in PZT, it's very interesting for filters and some other applications at high frequencies in a gigahertz range for communications. Now, relatively, I will spend some time talking about aluminum scandium nitride. Aluminum nitride is has a Wurtzite structure, 6 mm, and until relatively recently, it has been only used in its pure form. It cannot be made easily in form of single crystals. As a ceramic, it would be useless as a piezoelectric material. It's polar, but not ferroelectrics, so you cannot polarize it. You cannot make ceramics with randomly oriented grains piezoelectric, but you can do that with the thin films, and just like zinc oxide, which has same structure, it would grow in these column-like structure in which majority of the grains are oriented in the same direction, and you get some polarization. And then I think around 2009, it was proposed theoretically and discovered experimentally that if you start putting scandium in a Wurtzite structure, that piezoelectric coefficient starts increasing by a factor of 5 or so, which is huge, 500%, up to about 50% of scandium, and then drops down to 0. Now, this is very interesting. Rock salt, the aluminum, the scandium nitride, it has a rock salt M3M structure, and is not piezoelectric. You see, you get a 0 piezoelectric coefficient here. And this looks exactly like a morphotropic phase boundary that we were discussing before. And that's why I'm spending some time on this material. So this is rock salt structure. This is Wurtzite structure. So this is very interesting because this material, this is a different type of a morphotropic phase boundary. You remember morphotropic phase boundary in PZT or morphotropic phase boundary in PMN-PT. They both look something like this. This is rhomboedral, this is tetragonal, cubic, rhomboedral, tetragonal, cubic. This is ferroelectric with polarization like this, ferroelectric like polarization like this, and the same thing here in a PMN-PT, polarization like this, polarization like that. You may have some monoclinic phase here. Okay. And we explained that because of the flattening of the free energy, we have easy polarization rotation, and that gives us large shear coefficients and so on. Here it's different. Here we have a polarization in this direction and 0 here. So it's not a question of polarization rotation. Here we are talking about polarization extension and contraction. So it goes from 0 and then it softens for contraction of polarization. It could have some, of course, rotational character, but with respect to this boundary, it's from 0 to some other value. The similar principle has been observed in magnesium doped zinc oxide. Zinc oxide itself is polar and piezoelectric material, but if you add magnesium at some magnesium oxide is rock salt structure material that is not piezoelectric, but if you start adding it to magnesium, to zinc oxide, it will start increasing its piezoelectric coefficient, and then it also goes through morphotropic phase boundary. So we have this type of a morphotropic phase boundary, which is very interesting. We have some destabilization of the direction of polarization as it goes from this structure to this structure. It's complete reconstruction of the structure, and this increase in the properties is indeed remarkable. Now, just last year, this group in Germany was able to show that ALN, when you start adding scandium, in fact, becomes ferroelectric with a large amount of scandium. So scandium destabilizes the polarization enough that you can switch it. You remember our definition of ferroelectricity. Ferroelectric materials are those materials which have spontaneous polarization and which can be switched by electric field to another stable position. Okay? So any pyroelectric material is potentially ferroelectric. Maybe we just cannot apply large enough field to switch the polarization. So if you add something, some defect, some substitution, maybe you can destabilize that polarization and you can switch it in the opposite direction and still have that new direction stable once you remove the field. And that seems to be the case here for scandium doped aluminium nitride. They showed that you get nice square loops with huge coercive fields. For comparison, here is PZT. And PZT has a coercive field of about 10-20 kilovolts per centimeter. Here it's orders of magnitude higher. But in thin films, and you can make this material only in form of thin films to be ferroelectric and piezoelectric. Ceramics are easy to make, but they would be neither they would not be piezoelectric unless you can pole them, and so this gives us hope that this might be possible. However, since such huge coercive fields are necessary for switching, I think this will be only possible in thin films. This is still very interesting, well, from scientific point of view, that we can induce ferroelectricity. And second, from the practical point of view, sometimes when you make aluminium scandium nitride, these grains will grow in a columnar structure, but the distribution of polarization up and down would be about 50%. So you get very low piezoelectricity if you don't grow it carefully, if you don't control nucleation carefully. Now that we know that they are ferroelectric, we can apply electric field, and these sort of coercive fields can be easily reached in thin films. These materials shouldn't show high conductivity, and this might be possible. So that ends this section here, which came almost as a digression. And next we will start talking about other piezoelectric materials and applications.